square, I'm substituting this into this. So that substituting the value of lambda square, I will have this expression d square by dx square, second derivative of psi of x plus. Once you substitute, you will see that it will be 8 pi square m by h square into e minus v into psi of x. So this is nothing, just I am writing instead of in the wave equation, just I substituted for lambda using the de Broglie relation. So I got a second order differential equation. And this I can rearrange. It is up to you on what way you want to use it. But this is okay, second order differential equation we got, but usually it is expressed in all the books in this form, so that we will have this is h psi is equal to e psi form. So this is nothing but the same, but instead of an equation, here I am just writing it just like a kinetic energy part is acting on this, potential energy part is acting on this, like that. So this we can get it from the Schrodinger equation. So this is a time independent Schrodinger equation. So time independent Schrodinger equation, we are just getting that from the classical wave equations, although the time dependent Schrodinger equation is more fundamental one. And this is for the one-dimensional one, minus h cross square by 2m d square by dx square psi of x plus v of x psi of x equal to e psi of x. And for 3 dimension, instead of this is, you can easily see that this is in 1 dimension because x small x is there. But if it is 3 dimension, you will have the second derivative along x, y and z direction. So instead of that 3 directions writing separately, we will use this del square. Del square, that is nothing but partial d square by dx square plus partial d square by dy square plus partial d square by dz square. You have to act on each of these directions separately. It is a sum of this. Okay, so this will be acting on the psi independent for each and every directions. So this is if you want to write it in 3 dimension, we can write the Schrodinger equation, time independent Schrodinger equation in this form. At least one of them you have to remember. Next, time independent Schrodinger equation from time dependent Schrodinger equation. We can get the time independent Schrodinger equation, whatever we wrote here, that we can get it from time dependent Schrodinger equation. First itself we introduced the time dependent Schrodinger equation. We will see how it is. This is very interesting and important also. But it's very simple. I'm not looking for the, I mean, you have to remember all the steps involved in all these things. I'm not looking for that. But finally, the concept will be very final concept that we'll be using later. Okay, for that only we are, I'm showing all the derivations. Steps. Yes, please. Please.
In the Schrodinger equation, instead of using x, y, z, why are polar coordinates not used?
We will use later. We will use it later. Okay, so that will be coming. That will be coming. So you know that it is always easy to start with this x, y, z coordinates. So that is why everyone is familiar, comfortable with that. Later we will switch to polar coordinates. This is our idea is that a time dependent Schrodinger equation. So the time dependent Schrodinger equation is IH cross d by dt of psi of x. This I already showed you in the beginning when I introduced this Schrodinger equation. So this is the case. Okay, let it be there. Now what we will do is we are trying to get time dependent, time independent from this one. For that, for the time being, let us think psi of xt, that psi is a wave function, that is a function of position and time. Now we are splitting into 2 terms. One is explicitly, that is a product of one function that depends only on position and another function that depends only on time. That means we are writing our wave function as a product of one that is purely on x and another one that depends on time. That means we are splitting our function into 2 parts. One explicitly on position and another explicitly on time. So our function we are writing into 2 parts. Now differentiating with respect to time. This wave function, let us this function, whatever it is given here, let us differentiate that with respect to time. So I have this one. So I will be doing that differential with respect to time. So on the left side, I'm doing that d by dt of psi of xt, d by dt of psi of xt. So you remember that psi of xt is equal to psi of x into f of t. Okay, so I will have d by dt of psi of x into f of t. D by dt of psi of x into f of t. But you know that psi of x is a function of x alone. So when d by dt act on this product function, one is a constant for that. So that in principle you can take it outside, irrespective of whether you are doing multiplying with the first or second, that it doesn't matter. This is a constant for that. So once again, I'm telling you, we have the time dependent Schrodinger equation, and we are writing that as a product of two functions. One depends only on position and another depends only on time, and differentiating with respect to time. So as a derivation point of view, you may think why I am taking d by dt and all. Nothing. It is already there in the equation. So I'm just doing accordingly. So here you can see d by dt on the left side. So that I am doing. So d by dt of this function, when this acts, this is a constant, so this is that. So d by dt is acting only on the time part, function that depends only on time. So d by dt of f of t into sine of x, or sine of x into d by dt of f of t. So this part is over left hand side. Now on the right hand side, we have second derivative, but that differential is with respect to position. So here I am doing the differential with respect to x. So the same one I am differentiating with respect to x. So as usual, as I did in this case, I will be doing the differential on the right side also. So d by dx of psi of x into f of t. So in this case, you know that when I do d by dx of psi of x into f of t will be a constant. So that will be that can be taken first, or second, or it will be a constant multiplication only. So d by dx of psi of x is equal to f of t into d by dx of psi of x. But in this case, I will do a second derivative, because in my right side you can see that second derivative. So if I do that second derivative, d square by dx square of this one, again f of t is a constant. So d square by dx square of psi of x is equal to nothing, a constant multiplied with the second derivative acting on the function. So f of t into d square by dx square on psi of x. So I have some derivative on the left side, some derivative on the right side. It is not a sum. Sum means SOM is sum, because that I am doing with respect to whatever it is there in the equation. Now I got these expressions. And these two, first derivative and second derivative, I am substituting back in this equation. Okay, so if I substitute back into that equations, you can see that IH cross partial d by dt of psi of xt is this one. So IH cross d by dt of f of t into psi of x, left side. Right side minus h cross square by 2m, that is there. Instead of d square f of d square by dx square of this, I will substitute this one. So minus h cross square by 2m is a constant, and moreover f of t is also coming. So f of t, that is there, minus h cross square by 2m f of t. Then d square by dx square of psi of x plus v of x, then psi of x t, just I am doing f of t into psi of x. So this v of x is a general potential energy term I am writing. So I am not considering its time dependency or independency, just I am taking it that potential as such. Okay, so v of x, again that is psi of x. Instead of psi of xt, I am writing these two terms. So this potential may or may not be depending on that the time. Now I have this expression. My idea is to get a time independent Schrodinger equation from this one, starting from here. Now for that, to make that equations very simple and all, next I will divide throughout by psi of x f of t, so that many terms will cancel. you can easily see that if I divide by psi of x f of t, in this case psi of x is a constant. So if I divide by psi of x, automatically that will cancel. Similarly, many terms will cancel on the right hand side also. So remember this, what I'm doing is that here I am dividing throughout by psi of x into f of t. I'm giving enough time to explain how each and every step is coming from the previous one. And moreover, after today's lecture, I will give you the notes also. But I don't think I am giving a lot. I'm explaining several times how it is coming. So it's okay. So psi of x f of t, but just instead of just I did this, I did that and all, I'm telling why I am doing that before doing. So divide psi of x f of t. So if I am dividing psi of x f of t, this psi of x from the left hand side will cancel. Similarly, f of t will cancel from here. That there is a purpose. That is what I'm telling. So if I do that, I divided in the previous slide. So I will get I h cross 1 by f of t d by dt of f of t. What happened here, psi of x is cancelled, but I am dividing by f of t. So that is coming in the denominator. So that is the only thing on the left side. Similarly, on the right side, f of t, when I divide by psi of x f of t cancelled. So what I have, 1 by psi of x is there. And on the second term of the right hand side, psi of x, f of t, both cancelled. So I have only v of x term. Okay, so this I have. Now you can see that this is very important. This step is most important. The other things are just mathematics. Took the first derivative, second derivative, divided, and so on. Now, what is special about this equation? That is what we have to note. Here you can see that on the left side, this is a function of time alone. This is a function of time alone. Very, very important. This is a function of time alone. You can see that it is very clear. And what about the right hand side? Right hand side is a function of x alone. That means right hand side is a function of position alone.
So are you assuming potential energy is also only a function of? Are you assuming potential energy is only a function of space and not of time?
Here you can write, in this case, potential energy, I am considering it as a, I mean, in this particular case, position only, because right hand side. Otherwise, I cannot say like this, function of x alone.
That's what my question was.
Yes, yes. Otherwise, it cannot be. No? So this is a function of x alone. Now, moreover, still they are equal. This is very important. Still they are equal. This is a function of time alone. This is a function of x alone, and still they are equal. How this is possible? This is a question to you. Left hand side is a
function. If function will constant.
Yes, exactly. This is possible only if this is equal to a constant. Otherwise, it cannot be. One side a function of one variable, another side a function of another variable. So that means this is a constant, then only this is possible. And this constant, we can say that it is energy E. Okay. So this is this constant that is equal to E. So this we have, and if that is the case, now we will go one by one, because we have A equal to B equal to C. Then I can say that A equal to C, B equal to C. Just like that, I will go for that. So if I took in that way, first I am taking the right hand side equal to A equal to B equal to C. First I am answering B equal to C because of that is our main aim. Okay, so in this case, I have minus h cross square by 2m 1 by psi of x, d square by dx square psi of x is equal to blah, blah, blah like that. Okay, this I got. Now, still it is not in the form whatever we earlier discussed, but that needs a small modification. What is that modification? You have to multiply throughout by psi of x. So if you multiply, very simple mathematics, if you multiply throughout psi of x, this psi of x in the denominator will cancel. But as we are multiplying, when you multiply, you have to do it throughout the equation. So if you do that, you will get minus h cross square by 2m d square by dx square of psi of x plus v of x psi of x is equal to e psi of x. So this we got it. Okay, so this is what we were looking for. That means a time-dependent Schrodinger equation. We can get it from Sorry, time independent Schrodinger equation, we can get it from time dependent Schrodinger equation. So we got one part of that. Whatever our purpose, that is solved, but we are not stopping here. This is what our title was, time independent Schrodinger equation from time dependent Schrodinger equation with some simple mathematics we got it. So that means just they are related to each other. Now I'm not stopping here. I will go with it because we already told that okay, this is equal to a constant. So A equal to B, B equal to C. So A equal to C, B equal to C, that equation. So here I considered only one side, one part. No, let me take the other side also. Let us consider the other part also. If I do that, I will get this part also, A equal to C. So I h cross 1 by f of t into d by dt of f of t is equal to E. I got this also. Why I am doing is actually for the purpose that was enough. Previous slide was okay. Why I am doing this? Because this will give some other informations also. So I'm considering A equal to C part also. Again, just rearranging the things. IH cross, if I am taking to that side, it will be 1 by IH cross. And you know that if you solve it, you will get minus IE by H cross. This IH cross I am taking to this side. So it will be 1 by IH cross. Then you can multiply both sides and you will get this. Minus IE by H cross deta. Now this is a dft by f of t. dft by f of t is equal to this and so on. There are a lot of mathematics you can do. So here if I integrate this equation, if I integrate this, you know that it is nothing ln f of t. ln f of t is equal to minus IE by h cross t, because here I am integrating. Okay, so dt becomes t. So ln f of t is equal to this expression I got, and I am looking for f of t. So in that case, if I do that f of t, that means I have to take that exponential. So f of t is equal to, there will be a constant of integration. So that is e to the power of c, then e to the power of the rest, first term from whatever it may be. And exponential to a constant, that will be another constant. So I'm just writing a. So f of t is equal to a constant into an exponential function, that is exponential minus IET by h cross. This. So, sorry. Yes.
Sir, like you said that E is constant, so but the E should also have a dimension. Like if T and X were constants, E should have dimension, but you were saying that it's dimensionless.
No, this is a constant integration constant. No.
No, sir, I am talking about E, the above one E. You said that it's a constant, but energy is having a dimension. So, and you said that E is energy.
Energy.
So capital E.
But that will cancel. You can see that. That will cancel. That will be a number only.
Okay, sir.
So here we will get f of t is equal to e to the power of minus IET by h cross. Why this is important? This is important because the constant can sorry, I forgot to tell this. Here I am dropping that constant because this will be a part of our wave function. Ultimately, we have to normalize that wave function. So this is a part, even if it is whatever be the constant, that will be taken care of that time. That means when we write the total wave function, this constant we need not to carry all the time. That time it will be taken care of along with the other part of the wave function, or during the normalization this will be taken care of. So we are dropping this a. There is no point of taking care of that particular because as such the wave function we are normalizing, not the individual terms. Okay, so there is no point of carrying this. The other part is more than sufficient. So we got psi of xt is equal to what we, because in the previous example we wrote that the total wave function product of time part and position part. So I am taking that back. Psi of xt is equal to e to the power of minus IET by h cross into psi of x, or psi of x into f of t. So f of t I am using this. So if it is required, I can normalize these wave functions, but that depends upon system to system whenever I want, but not here. Or otherwise also I have no problem. If I want, I can multiply with the n of that. But the normalization constant, we are interested only on the functional part, because wave function ultimately for any system we have to normalize at the end depending upon the conditions. So here what we did, psi of xt we are writing as two part, one an exponential part and a position part function depending on position. Now, if yes.
Sir, the question is that so you mean that this psi xt when integrated from minus infinity to infinity will give 1?
Psi of xt, yeah, we depending upon the yeah, in this case we can consider minus infinity to plus infinity.
So that a there is the normalization constant.
Here no, a as such is not a normalization constant. To make this psi of xt to normalize, automatically another normalization constant n will come there. So that is more than sufficient. Individually we need not normalize.
A will merge into the wave equation, wave function.
Yes, exactly. Its effect will merge into this.
Okay.
So
Yes, please.
So from where the minus sign is come?
Where?
What is the reason of that minus sign?
That is a mathematical requirement. You are asking where this minus is coming. This minus.
Sir, can I tell?
Yeah.
Yes, sir.
Multiplying
So
I both sides, so I square will become minus 1.
This side. This is you see I h cross, you take these two sides. So what it will be? It will be 1 by I h cross now.
Yes, sir. So that one is iota.
Yes. Always remember this I, whatever I am telling, it is iota. Complex number में आता है ना, yes, same. This I already yeah. So again, if you this is for all. This I is that root of minus 1. Okay. So
sir, can you please re-explain what you were telling about normalization in this derivation, please?
No. What I'm saying is that what is our psi of xt? Psi of xt has a two parts, this part and this part. So overall, we have to normalize this wave function. So if you normalize this wave function, automatically a normalization constant will come here.
Yes.
So that normalization constant, when you use that, irrespective of whether you use a or a here or not, it doesn't matter. Because suppose even if you are taking a into consideration, I have no problem. I don't want to drop it. If you have doubt, you write a here. So what will happen here? Here it will be a into e to the power of minus iet by h cross I of x. Right?
Yes, sir.
Now I want to normalize my psi of xt. Okay, so that time I will be doing integral minus infinity to plus infinity n and so on. N will be there and your a will be there. But finally the new normalization constant, whatever you consider, that will be just like an multiplied or divided or scaled one with respect to this a.
So basically you're saying you have defined a constant divided by a constant, a new constant kind of.
Exactly. Thing. Yeah. I need not one constant or another constant. So that is why I'm not carrying.
Okay.
Even if you take here a, I have no problem. What I'm saying is that even if there is a constant, again I will have to find out a new constant. The value will be different. I agree. But the what I'm saying is that according to me it is a constant only. Scale factor you can tell. Okay. Now if you take its square. For example, psi of xt, now you take its square because we have this wave function. Now you take its square. If you take its square, again, please remember that this is conjugate I'm telling. So if you take its square, so here moreover you can see that imaginary function. So you have to take that, no doubt at all. So in this case, if you take conjugate, so it is very clear why what is mean by psi conjugate. So if I take the conjugate, it will be e to the power of iet by h cross. Iet by h cross, because of minus will become positive. So I have e to the power of iet by h cross into then as usual the function also. Now you know that e to the exponential iet by h cross into exponential minus iet by h cross, you know what it will be, and into this part also psi. If it is, we don't know whether that is real or imaginary, so I am just carrying again psi of part. So you know that this is e to the power of 0, exponential 0, and that is equal to nothing. You know what it is. So the probability density, you can see that psi of xt, you see psi of xt, the wave function is a function of time. The wave function is a function of time, but its square, if you take it, that is independent of t. That is independent of t. This is very important. The probability density is independent of time. The probability density is independent of time. These are some special kinds of states. They are called stationary states. That means the states for which the probability density is independent of the time are called stationary states. You see this for some students, this may looks very again abstract. ये क्या है first day से abstract things बोलते रहते. You may think like that, but this statement, you read it, even if you feel like that, read it very carefully. The states for which the probability density is independent of time are called stationary states. What are stationary states? One should know that, because its probability density will be independent of time. Such states are called stationary states. This is very important. That is why when we consider a p orbital or an s orbital or d orbital and all, they are stationary states because the probability density is independent of time. Otherwise, it will be a big problem. You cannot tell that p orbital one part an electron is there. Now it is there. After 1 second, there is no electrons. We are not talking like
Excuse
that.
me, sir.
Yes, please.
Sir, in like why मतलब all states are not stationary states. मतलब ऊपर हमने derive करा उसमें तो e towards 0 time के independent आ ही गया probability density.
No, not all states. No, I didn't say all states. Stationary states, only all the stationary states. If stationary states are in the probability density will be independent of time. If it is depending on time, if some states depends on time, then they are not stationary states.
लेकिन सर इसके ऊपर तो हमने प्रूफ करा कि टाइम के इंडिपेंडेंट होता है प्रोबेबिलिटी डेंसिटी.
Sorry, can you speak slowly? I can understand Hindi. I can talk in Hindi.
In the
If
above
you are
sentence,
very fast, it's difficult for me.
yeah,
Tell me.
in the above sentence, we just proved that the probability density is independent of time.
For this particular case, I'm not telling for all states. I'm not telling for all states.
Okay, sir,
If
okay,
it
sir,
is
okay.
coming like that, if some particular states are coming like that, then only I will say that they are stationary states. If it is not coming like that, if some states, if they are not coming like that, they are not stationary states.
Okay, sir, got it.
Not for all.
Sir?
Yes,
This
last
Schrodinger
question. Last question.
There is
Yeah,
a Schrodinger equation trying to associate itself with the probability density.
Sorry.
Is the Schrodinger equation kind of associates itself more to the probability density than the wave function? Because even in the time independent one, the wave function has a time component, but the probability density is the one which does not have a time
independent of. It is independent of time.
Okay.
So, stationary states. Now I told last question. Now we will discuss only after the class. You have to wait. If you have, because enough discussion is done, and moreover one question was helpful for others also. So please let me continue and to finish the target whatever I had. So now you have to ask in the last. Okay, stationary state doesn't mean that the particle is at rest, because we always, when we take the word meaning, sometimes you will be confused. Oh, stationary, okay, dead. No, nothing like that. Stationary state doesn't mean that the particle is at rest. The probability density is stationary and not the particle or system. Again, this is anyway, that is given in red also. The probability density is stationary and not the particle system. That means if you look at the probability density, always it will be there. That will be, that will be stationary and not the particle or the system. Probability density will be independent of time. That is why when we take a p orbital and all, we tell that the probability is maximum at the, you would have seen a p orbital. Where is the probability maximum? At the center, there is no probability. Probability maximum is somewhere. That is not keep on changing. That is not changing. And also when we write a node, when we draw a node p orbital, probability density is there on one side and other side. It doesn't mean that the now the electron is in this lobe. Later this electron will be in that lobe. There is no such meaning. We are talking about probability density. That means in quantum mechanics we will be talking only about the probability density, not the trajectory, how it is gone from here. It is there, but how there is a space somewhere in between. If you take that p orbital, there is a node, there is no electron there, but at the same time we are talking about electron density on this lobe and that lobe. So obviously this question comes, what electron density is there, electron density is here. I'm not telling that electron is moving from one lobe to another. I won't tell that. I'm telling that probability density is there and probability density is here also. So stationary state doesn't mean that the particle is at rest. It is just telling that the probability density is stationary and not the particle or system, because particle cannot be at rest, because then it is a violation of uncertainty principle. So here the purpose is that for stationary state, if you take its a square probability density, you will see that that is independent of time. That's only. Next is a new model. This is very important model. Now onwards, up to here, okay, today's first part of the lecture is still okay, because there I was talking about if you have a quantum mechanical system with the time, how it is evolving and all. Now from this topic onwards, especially this topic onwards, we are entering into the new, I mean, little bit physical significance, we can say. There are, we may easily correlate. So those who had some issues with the previous 1, 2, 3 lectures, they may not face that much problems from this topic onwards, because these are something we can correlate to our many of our systems or properties and so physical properties. Okay, so this is one of such systems, and moreover, that is most important. Moreover, from this topic onwards, from this particular system onwards, whatever we will be discussing, there we will be applying all the principles or the postulates whatever we studied or discussed earlier. Now when these models, we work on these models, then all the things whatever we discussed in the last 2, 3 lectures will be more and more clear. So I will suggest, when we go through these topics, again go back and read. Then you will get what we discussed earlier. In the first attempt you may not get, now you may be a little bit confused and all, although I tried many, I mean I tried to answer your queries and all, but with these models you will see that we are applying all the principles or whatever the normalization, orthogonalization, all those things. So you have to keep on going back and read it and come back. Then you will see that, okay, all those things are clear, or whatever we discussed so far. Now, again, in quantum mechanics, this part I am telling particle in a one-dimensional box. In quantum mechanics, we will have different model systems. Again, please remember, I will be discussing about model systems. Model systems are not real systems. Okay, model systems are not real systems, but still these model systems are very good, so powerful that can easily correlate with the real systems. Okay, particle in a one-dimensional box, this is a model system, and we will have some real systems that we can connect to this one. Okay, so we will be discussing 3, 4 model systems. and each and every time I will be connecting with the real systems, so that you can easily understand the model system. So why this model system is required, how it helps and all. And moreover, in quantum mechanics, this is one of the best and simplest model systems, but its a consequence is a very important one. Very important one. Whatever the principle we are getting or the conclusion we are drawn from this particular model. Okay. So, for example, just I wish not to discuss much on the word meaning of that. Okay, sometimes it is better not to discuss much and think a lot on certain things. So here I will not go for word meaning of each and this particular model. That is not required also. But only one thing I just want to emphasize, that this particle in a one-dimensional box is the first, best and simplest models in quantum mechanics. Okay, so let us see what is this, what is mean by particle in a one-dimensional box. You may not have any problem to think about a particle in a box. Consider a box, keep a particle, that's only. So that is why I told this is a model system. In a box, you have a box and there is one particle in that. I'm not telling what is that particle. It is up to you to decide whether it is an electron, whether it is an atom, whether it is a molecule. It is up to you, or anything else. I have no problem. Okay, so particle in a one-dimensional box. Okay, what it is? As I mentioned, this is a model to illustrate the quantum effect. Very important result you will get it once we solve these equations, once we solve this model. Okay, wait. So this is a primitive treatment of the conjugated molecules. I was not supposed to tell this. I was not supposed to tell this because this is one applications we can talk about this. But this application is very not very fine one, but very crude one. But still, to make as a chemistry point of view, I just want to tell this it in advance itself. Okay, before starting itself, okay, this can be considered as just like a conjugated system, some kind of properties related to conjugated system. You may be knowing that conjugated system, what I mean by conjugated system. I'm talking about the chemistry, butadiene, 1,3-butadiene. That is a conjugated system, single bond, double bond, single bond, double bond, then 1.5 bond, like that. 1.5 means neither single bond nor double bond because of delocalization and all. So in that kind of system, conjugated system, we can use this, its applications we will be using there. Okay, this models result we will be using there. Anyway, this is not the, actually this is not good to mention here because the purpose of particle in 1D box is not to study the conjugated system. Once again, I am repeating, although I am giving this example or the result or application, the beginning itself, the purpose of this model is not for this purpose, not for this. Okay. Okay, what it is, that we will wait and see. Okay, let us see. Let us try to understand about this this model. What is mean by particle in a 1D box? So we will make just like a skeleton today because we won't have enough time for to complete this particle in 1D box today. So this model's skeleton we will make. The life we will give it in the next lecture. Okay, so today we are going to make a skeleton for this model. So what is this model is? So this model, particle is moving in one-dimensional box of length A. Okay, so here this is a box and its length is A. So length is A means its boundary is x equal to 0. This is the place x equal to 0 and this is x equal to A. So this is a box, one-dimensional box I'm telling, and two boundaries I have, x equal to 0 and x equal to A. So forget about this. Close your eyes and think about a box. A box has two edges. A box will have several edges, but I am telling this in this case one-dimensional box. So two edges you consider along one direction in that box you consider. So that is x equal to 0 and the other end will be x equal to A because the box length I am considering as A. Okay, so the particle is now consider a particle that is moving in that one-dimensional box of length A. Now there are some conditions I am putting in this. This is something different from your box. If you consider a box, you cannot accept this condition whatever I'm putting. Okay, so to that particular box I am giving some conditions, certain conditions or restrictions I am giving. What are those conditions or restrictions? I'm telling you that inside the box, inside that box potential energy is 0. Inside the box the potential energy is 0. Outside the box, the potential energy is infinity. This is one condition I am putting, restriction I am giving. Inside the box, the potential energy is 0, and outside the box, the potential energy is infinity. Okay, you know that this is not possible for a real system. That is what I told. This is not a real system. This is a model. Okay, so in this model, but this model is, although we are giving this many restrictions. Although we are giving these many restrictions, the outcome is unimaginable. Okay, so particle is moving in a one-dimensional box of length A, and we are giving the potential energy equal to 0 inside and V equal to infinity outside. Now we are writing the Schrodinger equation for the particle outside the box. This is what I told Schrodinger equation. We will be to solve any models. We will be discussing 3-4 models in this course. In all these courses, all these models, the only thing what we will be doing is we will be writing the Schrodinger equation. Okay, so in this case also I am writing the Schrodinger equation for the particle outside the box. You read it. What I am telling, Schrodinger equation for the particle outside the box. Already my problem itself is particle in a box. But now what I am doing is Schrodinger equation for the particle outside the box. Let us see, wait and see. So this is the Schrodinger equation, minus h cross square by 2m d square by dx square into psi of x equal to E minus V into psi of x. E minus V into psi of x. This is our Schrodinger equation. Although you don't remember this, you may not be remembering this because today only I introduced the Schrodinger equation. But it's okay. Trust me, this is the equation I showed you. Minus h cross square by 2m d square by dx square. Psi is equal to E psi. E minus V into psi. That is the equation. So E minus V, but here V is infinity because I am considering the outside now, not inside, outside. So V is equal to infinity. So I substituted E minus infinity into psi of x. Now you know that E minus infinity, that is equal to infinity because a small value that you are subtracting from infinity, a small value minus infinity, that will be also infinity. And there is no significance in that case if I am considering that V as infinity. So now simple mathematics will drop these two minuses and all, and this I can take it to that side and all. But again, what is the use? You are multiplying infinity with h cross square by 2m. That is again infinity. Infinity, whatever you multiply, it will be infinity. Okay, there will be some difference, but compared to infinity, you don't know what infinity I am considering now. So with respect to that, we can consider it as infinity. So this equation is nothing, d square by dx square of psi of x is equal to infinity psi of x. We got that. So what? Yes.
E is the kinetic energy of
Which one?
E
is the total energy. E is the total energy.
Sir, so if V is the potential energy, so E would be the kinetic energy plus the potential energy. So E would also be infinity. Why would it be a small number?
But I am considering that just I am taking as a number. Whatever you see, I am talking about the energy of that particle. Energy of that particle.
If V is infinity, E would be a bigger infinity than it now. So how can
you see? I understand your question, but instead of that number, forget about whatever be the value of that number. The particle is inside. The particle is inside. That has a particular energy. Whatever be the energy. Now I am considering whatever be that energy. Now outside I am considering that particle. So actually I don't want to use tell that the particle is not at all there. But still, if I consider the particle with energy very high value, instead of considering that, one second. 1 second, please. Kinetic energy minus potential. Let me write it. Minus h cross square minus h cross square by 2 minus this is total energy only. Now your question is that if I consider photon, that cannot be particle kinetic energy. Okay, I will think about that your particular question later. For the time being, let us take it as infinity. Okay. Thank you for that question. I will think about that because I don't want to stop it right now and stop the entire class. I will answer to you. Okay.
Okay, sir. Okay.
So for the time being, you take it as a number. Right now, I don't want to think about that or substitute or anything. For the time being, you take it as a number, and then in that case, it will be infinity. Because I wish to instead of a number or something like that, or I mean concept, I have to bring it so that I will come back to you. Okay. Sir, so for the time being, let me complete. Yeah. Someone is asking.
Sir, please repeat second equation.
Second equation. This one.
This
I'm just telling that if you have a high value of E minus high, this is a small number. Take it as a number, whatever it may be. This number minus infinity you have. So total it will be infinity. That's only.
Okay, sir.
This is simple. Certain questions you are not supposed to ask also, not to a particular person. I am telling the entire class. You just work it on that so that we can continue. Otherwise, we will stop in each and every step. This you try because I think that you can do once you have this expression and all. Anyway, now it is clear now how you got it.
Yes, sir.
Want to ask the question? Okay.
Yes, sir.
So d square by dx square psi of x is equal to this we got. Now you can write psi of x from here. So psi of x here. So I'm taking this to this side. So it will be 1 by infinity into. I'm sorry that I'm not doing whatever it is in the right side. When I take it to left side, in principle, I should have write this expression first and then equal to psi of x. I'm not doing that, but that at least that you have to do yourself. Okay, because the reason is that although I'm taking this infinity to this side, I don't want to write this expression first because my aim is to get the expression for psi of x. So even if I do that again, I have to rewrite the equation and all. But so that much steps I don't want to write. Some steps I want to skip it. So I hope you will not have any issues to get this equation from the previous equation. Okay, so psi of x is equal to, you will get 1 by infinity into blah, blah, blah like that. That means simple mathematics. Now you know that 1 by infinity, we can take it as 0 or what it is. Psi of x is equal to 0. You got a psi of x is equal to 0. Now, if a psi of x is equal to 0, what is the meaning of that? What is the meaning of
that place is 0 because more the phi.
Yes, exactly. Psi of x is equal to 0. That means the particle is not outside. The particle is not outside. Then you may be thinking what nonsense I am doing. Already told that we are running late, but still Sir is talking about particle in 1D box and proving that the particle is not outside. Okay, so for those people, I hope all of you can read Hindi. Otherwise, you can convince your friends what is the meaning of what it is written. There may be small spelling mistake, but that you forget about. So this is what. So I hope you understand.
Sir, I had one small question.
Please, no comments right now. No comments at all. So please read whatever it is. So if this is your question, whatever it is written here, my answer is this. Your question is again this. My answer is that you have to wait. Okay, that will continue in the next case. The idea is that we are telling that particle is inside, but first is itself what we did was that we proved that the particle is not outside. This is a requirement. There is a reason that we will continue in the next class. Okay, so we know that we
Yes.
are discussing about a particle in the box, but we are proving first itself that the particle is not outside. Although it is a really useless thing, but still we did it. But particle in 1D box, we will continue in the next class, already late. But somebody was asking one question. The others can leave. And the one who was asking some questions while I was showing this, he can ask the question.
Sir, aren't
questions
we
actually.
putting a wrong
First of all-
restriction?
Sorry?
Sir,
Yes.
I was asking that aren't we putting a wrong restriction? Because we are basically saying potential energy outside is infinity. So how can the particle be there? I mean, it's wrong restriction.
But I am proving that there are cases you will see later. That is what I told. They claim. Okay. I know that is what I told. The particle is inside, but they are proving outside because of some reasons. For that, you have to wait.
Sir,
Yes.
that the first equation that you came out with for the wave equation, what is its source? Like the normal wave equation that we have in classical physics, that kind of wave equation?
The Schrodinger equation, whatever we discussed today.
No, the first equation after which we substituted lambda.
This exactly this equation, minus h cross square by 2m d by dx square, that equation. Before this means?
In which we substituted the Broglie.
You are talking about the particle in 1D box case.
No. The starting equation for the Schrodinger equation, in which we substituted.
You are taking in the no. I thought that your question is on particle in 1D box. Which one you are telling?
Yes, this
this is equivalent to, because wave equations, you know that is a function of time only, based on time. Similar equations we can start. That is what which one? Sorry, where it was?
I have to go back. Yes.
What is your question?
How come this wave equation is only dependent on the position?
No. Wave equation, it is a second order time equations that you know from that. I'm writing similar equations for that.
Okay, so what is the source of this equation, like which you have written here?
No, this is just how it was considered. I mean, the thought, how the wave equation was that similar equations he wrote. But I will check it. Any issues you find with respect to time, I have to check it. No, it is okay. Rewriting it will come. The idea is that although the what I will say, Schrodinger equation, the fundamental one is time dependent equation. Schrodinger historical point of view. He started from the time independent Schrodinger equation was derived. Proposed first. There is no derivation for that.
Okay.
There is no derivation for that. That thought process was just similar to that equations. Not there is no derivation for that.
हमें ये बेसिकली हमें बस मानना ही है कि ये होता है और उसके बाद हमें चीजें करनी है उसके साथ.
Yes, correct.
Okay. Sir, but this is the equation for SHM. Is it related to that?
Sorry.
This is equation is related to SHM.
Origin I will check it, because as far as I know, this is like concept was taken. That's only origin from where it was, because it was not just like a late it could connect, but this was there is no derivation for this. So exactly